Okay, perfect. So this presentation is about a book written by Jason Brownlee. More specifically, it's about time series forecasting with Python. Let me just start the slide right now. Little background about me. I do work in the tech consulting industry, mostly with Microsoft Azure, but let's jump into the more important stuff. So if you don't take anything away from this presentation, I do want you to take away one thing, which is this name, Jason Brownlee. If you do want to learn anything about machine learning, this guy is absolutely amazing, especially when it comes to Python. He's super, super productive. He has written more than 20 books or more. There are more PDFs, ebooks on machine learning. You can access them via this website here, or you can just Google him. He also has another website where he talks about Python in general. So I think he's based in Australia, but overall super, super productive human being, very, very smart. And I found the tutorial super helpful because it not only gives you kind of the theoretical background for statistics and machine learning, but he also actually implements everything he talks about directly in Python code, so you can kind of play around with it yourself and follow along as he develops the concept. So it really helped me as a beginner or an intermediate to understand machine learning with Python. But yeah, let's begin by talking about what time series forecasting actually is. In the literature, you oftentimes hear the word extrapolating. It's kind of an old word, but that's how people used to, or that's how people used to describe time series forecasting. Nowadays, you just call it time series forecasting. But in general, what time series forecasting is, it is you have data that is related to time. So as you can see here, compared to a normal ML data set, you have a time entry to each observation. That does seem pretty trivial right now when looking at it, but it actually causes all kinds of problems when testing and developing the model. Now, when looking at this graph here on the right, this is a pretty common way of visualizing data. So you have your old time series data, and then at a specific point you stop and you want to predict what's happening in the future. There are certain confidence intervals here, so you can make it look pretty. Depending on the problem you are given for time series forecasting, there are usually a couple questions you want to answer. For example, how much data is available? So in this case, we only have 8 or 9 data points, and I would say it's not that useful to predict that far into the future given only 8 or 9 data points. But I'll talk about this also more in a later chapter. You also want to look at how often you need to forecast. For example, do you need to forecast on a daily basis? Do you need to forecast monthly? So the frequency of your forecast prediction is very, very important to choose the right model. Obviously, another point is how far you want to predict the future. Obviously, the farther you go, the harder it becomes. And that's why you see how the confidence intervals is increasing over here. Let me lose one word about the tool used in the book. So most of the time, Brownlee uses pandas. I'm pretty sure most of us are familiar with pandas, but I do want to point out that it actually surprised me how many useful functions there are in pandas for machine learning and specifically for time series forecasting. So I highly recommend you guys to check that out if you're interested. I will point out, or I will try to point out as many functions as possible over these presentations. But if I would point out every function he noticed or he explains in the book, then there would be a presentation itself. So I unfortunately can't do this, but I'll do my best again to pick and choose the most useful functions to me at least. Next, I want to lose one word about this difference here, describing versus predicting. So time series forecasting, as the name suggests, is concerned with predicting, whereas describing would be time series analysis. So we are not concerned with describing what's happening here. We are concerned with what's going on in the future. And lastly, for this slide, I want to point out that there are 4 components to each time series. You have the level, the trend, the seasonality, and the residuals or the errors. And I will also talk more about each of those components in a later slide. However, what I do want to start with is how to actually get started on a time series data problem, because it's actually not that straightforward. In a normal supervised learning situation, you have input variables and output variables. Usually when you look in textbooks, supervised learning problems are always written in this equation. So you have an input variable x, and you're somehow trying to predict an output variable y with these input variables. So in this case, you have 5 input variables, and you have the output variables you're trying to predict. Now, when looking at a normal time series data set like this one here, you have input variables, but you don't really know what the output variable is. So somehow you have to restructure that data to make it look like this. And that's what a sliding window does. So the sliding window is a technique used in this book by Jason Brownlee to reshuffle the data. And it's pretty straightforward if you think about it. All you do is you're using the previous timestamp to predict the next timestamp. So in this case, your first timestamp becomes the input variable, and your second timestamp becomes the first output variable, or the second output variable in this case. However, you can't really use the first row and the last row because the data is not there. In Python, you can use functions for that. From pandas, I think it's called the rolling mean function or the sliding window function. I'm not exactly sure, but it's basically one function, and it automatically transforms your time series or your data frame into this structure. So it's pretty neat and pretty useful. So you can do it for the univariate case where you have one observation, or you can also do it for a multivariate scenario where you have more than one thing you're trying to measure. In this case, please note that you are not only using the first 2 measurements, you're also using the third measurement to predict the fourth outcome. So in this case, the first row we can disregard because we have missing data, but the second row is actually useful because we can predict the output variable, but we are using the first measurement, 0.2, the second measurement, 88, as well as the third one, 0.5, to predict the fourth, which is 89 in this case. But that's generally how it works, and you can use, like I said earlier, a pretty neat function in Python to do that, and it only takes 1 line of code, so it's not something very complicated, but it helps you tremendously to convert your time series data to a machine learning supervised learning data set. But yeah, that's just the background on how to get started. Once Brownlee talks about this, he goes into data visualizations. And the reason for why he goes into data visualizations is because whenever you want to pick a model, you first need to understand your data as much as possible. So that's why he introduces all kinds of different graphs you can use to look at your data. I've mapped a couple of them onto the slide. They're pretty straightforward. We have the scatter plot, we have the histograms. I really like them because they do show you how your data is distributed. We also have a heat map here. In this case, all these 6 plots are from a data set that that describe the minimum daily temperatures in Melbourne. So let me explain what's going on here with the heat map. So we have daily minimum temperatures for Melbourne over a 10-year period. So if you look at this heat map, on the row axis, we have the years from year 0 to year 10. And then on the column axis, we have all the days. So day 0 to day 360. And as we progress the year, let's say we pick year 4, we start in January. It's pretty warm in January, usually in Melbourne, because remember, they're on the south side of the Earth. And then as we progress through the year, it gets colder and colder over the summer months. And then in the winter, it gets warm again. But yeah, basically it's a standard heat map, nothing crazy. Another plot I really liked are the box and whisker plots. I've seen them in scientific reports before, but I never really found them useful. But now I actually do understand them, so they seem quite helpful to me. So what they show is, they give you each time interval on a yearly basis, and they show you where most of your data resides. So this box here is actually the 50th percentile of all the values. So it shows you that for this given year, the average temperature for Melbourne, or the average minimum temperature, daily temperature, was at around 12 degrees, and 50% of the time, this minimum daily temperature resides within the 8 to 14 degrees scale. And then it also shows you where kind of the outliers of your data are. So to me, it's a pretty useful plot because it gives you a lot of information about your data set. Okay, and then here on the right, we have some data visualization for autocorrelation. So first, let's maybe talk about the lag plot. With the lag plot, you're basically plotting an observation at a given time point, plus the observation that comes directly after. And what you can tell with the lag plot is how much your data set is correlated to each other, or how much autocorrelation there is between each data set. So the more linear this relationship here is, the more autocorrelation we have, generally speaking. So in this case, you can tell that there's quite a bit of correlation going on, which makes sense from a logical standpoint because you're modeling temperature. And if it's warm on one day, let's say we're in the summer, and then we expect that the next day will be quite warm as well. And this relationship can be confirmed indeed with the autocorrelation plot. So in this case, if you look at the time scale, we are plotting autocorrelation for all the 3,600 days over this 10-year time period. And as you can see, we kind of have this reoccurring seasonal pattern, which means that all the summer days are somehow related to the other summer days that come in the year preceding it. So it really makes sense if you think about it. Every 180 or every 360 days, we're kind of going a seasonal cycle. So that's basically what this autocorrelation plot shows right now. Yeah, but in general, these are just normal data visualization tools that help you understanding your data set. So now let's go a little bit deeper into understanding your data set and maybe changing it, depending on the problem you're facing. Oftentimes you want to rearrange the data. And to do this, people often use resampling and interpolation. If you talk about resampling, there is two ways you can resample. You can either upsample, which means that you increase the frequency of observations. For example, let's imagine that we have monthly data for temperature, but we want to have daily temperature. So what you can do is you can say, okay, I have monthly data for January, which is 12 degrees, and monthly data for February, which is 25 degrees. And you can interpolate these values in between by simply connecting the January data point to the February data point by a straight line. So that's what they've done here. Let's say this is the January data point and we have the February data point. You fill in all the missing data values, so January 1st, January 2nd, January 3rd, by a straight line. So it's basically connecting those 2 points. And downsampling on the other hand is the complete opposite. The textbook example would be you are working in a business case where you have monthly data, but for reporting purposes, you want to present it in quarterly data. So you're basically taking the mean of the 3 months that belong to one quarter to get the quarter data. So it's a pretty straightforward problem. And again, in pandas, you can use functions to do that with one line of code. So it's pretty straightforward. So this topic, power transforms, took me quite a while to understand. I didn't really know why the heck you would do that. So what they do is they remove the trend from a data set. I didn't really understand why you would remove trend from a data set, because I always thought, okay, the trend is so important to a data set that why would you remove it? But now I understand that you want to remove the trend from a data set because it's much easier to model after the trend and the seasonality have been removed. And then you model this removed trend or removed seasonality piece individually, and then finally add it to your original model again. So by doing it that way, step by step and individually, you are usually getting much more accurate models than modeling the entire time series that have trend and seasonality incorporated. So in this case, what I've done here, I've simply created a simple plot where I plot all the numbers from 1 to 100 squared. So as you can see, it's a perfect parabola. And then I'm taking the square root out of all these quadratic values to get a straight line. So as you can see here, I'm removing the quadratic trend and I am getting a linear trend out. Similarly, if I would have done a more exponential trend, so let's say x to the power of 3 or whatever, I could have used a log transform to make it linear again. Now, in theory, or this sounds nice, but in practice, obviously your data series is much more complicated than this contrived example. So what you can do, and what I recommend, is you use this Box-Jenkins transform, because this Box-Jenkins transform actually combines the square root transform with the log transform and picks and choose whatever fits best. So you can not only, it can't only pick the square root or the log transform, it can kind of combine them. So it automatically fits your data the best way possible. So you don't have to worry about configuring the log transform or the square root transform in any kind of way. So it's called Box-Jenkins transform, and I think it comes with the stats model library. So yeah, that's something I find pretty useful. The next topic Brownlee talks about is moving average smoothing. And I thought the time we're in, I had to include a COVID graph here, or Corona graph. Essentially what moving average smoothing does, it removes kind of the noise from your graph. So as you can see here, the orange time series is the original time series. And then the black graph is the smoothed out graph. There's two ways you can do it. You could either do a centered moving average, where you would, let's say, you would take your date, let's say April 16th, you would go 7 days into the past and 7 days into the future from that given date. So that would be a 2-week centered moving average, and you would calculate the average for all these values. And this would give you your value for April 16th. You can also use a trailing moving average, and I believe that's what they've done here. Otherwise, they wouldn't be able to display it right there, where you basically go 2 weeks into the past, find your average value, and then display it. But yeah, that's a pretty common technique to make your data look a little bit more smooth and not as noisy as it is right here. And with Python, I pointed it out here, you can use the rolling window size function to achieve exactly this. So you just specify the window, how much you want to go back and forward, and then you give another parameter of if you want to do the centered moving average or the trailing moving average, and it does it for you. So now, next, I want to talk about kind of the technical components of time series. As I mentioned earlier, there are 4 components, and you can further split them into 2 different categories. So you have systematic components, which are level, trend, and seasonality. In this case, the level isn't displayed here, but the level, essentially what it means is it's the horizontal value at which your time series resides. So you can think of it as a horizontal line you can shift up and down depending on what you want to do with it. The trend obviously shows in which way the time series is developing. As you can see here, from this data set, the trend is clearly increasing. I believe this is a data set from airline passengers from 1949 or 1950 to 1960. So it shows clearly that the number of people that are flying is increasing. And it also shows the seasonal component, the seasonality component, because people usually tend to fly during the holidays more than during the rest of the year. So clearly there's a seasonal pattern, and you can recognize it for sure right there. And then lastly, we have the residuals. One very, very important point I want to make about residuals is that, let's say you model your data and you run it on your testing set, and then you finally get residuals or errors for your model. You do want these errors to be white noise. I'll talk about white noise in the next slide, but essentially white noise is completely random error, and you want to have that in your model. Why do you want to have that? You want to have it because if you would have any kind of systematic component in your error, then this would mean that you can do a much, much better job modeling your data. So in general, it's kind of a quick check for you to see how good your model is if you look at the errors, and if your errors are white noise, then you've usually done a good job to incorporate all the components of your time series into the model. Anyways, there are also 2 ways you can model your components. There is this additive component where you basically add all the 4 components together, or there's a multiplicative model, and it kind of varies on your data set and your problem, which model applies to your situation, but Brownlee doesn't spend too much time talking about it, so I'm assuming it's not that deep and not that important. Lastly, the stats models library comes in clutch again at the end because it provides a very automated decomposition tool. Again, just 1 line of code that helps you to decompose a time series into 4 components, and it spits out it literally spits out 4 time series objects in Python. So very, very nice. Okay, so this slide, as announced, is talking about noise. Here, just a visual inspection of white noise. If you have white noise, this is how it will look like. If you ever get presented with a time series that looks like this and somebody told you to model it, I'm sorry, because you can't really do anything about it. It's white noise, it's completely random. Each value is not related to the next, but they somehow still are centered around a common value. In this case, the mean of the white noise is 0. Standard deviation is 1, which is pretty low, but whatever. You can check by visual inspection, like I just said, or you can check for basic stats type. For example, in this case, the mean is 0, which is a pretty big indicator for the fact that your noise is in fact random. But you can also check for other things in order to see if your data is not white noise. For example, if your data has a non-zero mean, it's usually not white noise. If your variance changes over time, it's not white noise. Or if you have any kind of correlation between values, it's usually also not white noise. So those are 3 pretty common steps for you to check if your data is not white noise. But yeah, that's just as a heads up, and hopefully you'll never have to deal with time series data that is white noise. So the next slide, this slide here, is talking about using and removing trend or seasonality. Like I mentioned earlier, it's very important to remove the trend and the seasonality from your original time series because it results in much, much better models. There are 2 ways you can do it. You can either detrend by differencing, which means that you are taking, for example, the observation value in the year 1960, and you are subtracting the previous value of it. So you would subtract the value at 1959 from it. And by doing this, you will get a graph that has much, much less trend and is much, much more stationary than the original graph. The second technique is called model fitting, which means that you are fitting a model on the data, and then you are subtracting, instead of the previous value, so you are subtracting the prediction from the original value. So that will also help you detrending your data. Before you do this, I always recommend to check for stationarity or for a trend in the first place. And the most standard test to do that is the Dickey-Fuller test. It's a common statistical test. It has null hypothesis and an alternative hypothesis. It uses p-values and t-values, so you can look it up and Google it. It's pretty straightforward and helps you to check if your data is stationary or not, meaning there's no trend or no seasonality. Okay, so now going back to slide 1, where I talked about how the time component can be a little messy in time series forecasting, we have to talk about evaluating models. And now you maybe realize how it's a little more difficult to test your data and train your data compared to normal machine learning problems, because for normal machine learning problems, you usually do a random train test split. So you completely randomly split your data into train and test points. And then you do a k-cross-fold validations where you basically do 100 different splits into 100 different intervals, and you train and test your models 100 times. In time series, you can do it, but you have to be very, very careful because you have to preserve the order of the observations. You can never shuffle around the order of your time series. So that's why in this case, you can see that even though we have different testing splits, so for example, we have a 50-50 split here in the first case, probably a 70-30 split in the second case, and maybe, I don't know what this is, an 80-20 split in the last case, the order is always preserved. So that's one thing I want to point out, that you can do k-fold cross validation, but you always have to preserve the order in time series forecasting. And then the third way of testing your model is the walk forward validation. So for example, imagine you have a model with 10 data points, you're testing it, and then another data point comes in, you're testing it again, another data point comes in, you're testing it again. So you're kind of walking forward to see how the score of your model develops. But yeah, those are the most common ways of backtesting your forecast model in or with time series data. So when you're testing it, you obviously need some kind of metric to evaluate it, and people usually use errors. Those are the most common errors. The forecast error obviously is the expected value minus the predicted value. You can then take the mean forecast error, the mean absolute error, the mean squared error, but most commonly people use the root mean squared error. But I'm sure most of you are familiar with this, so I'm not going to spend too much time talking about the underlying mathematical principles, but just as a heads up, those are the things people talk about when they evaluate the metrics. Okay, so now the grand finale of this presentation. Lev and I talked about this a lot. This is the ARIMA model, and we actually spent probably way too much time trying to understand this beast. It's also known as the Box-Jenkins model. And before I go into the details, I want you guys to know that This is interesting, but you don't really have to understand it. It's not that great of a model. Lev told me that there are other models that are much more valuable and easier to understand compared to this, but for some reason, Jason Brownlee really likes this model and he uses it all the time. So when talking about this book, we do have to talk about this stupid ARIMA model, how Lev would say. But anyways, the way I want to explain it to you is that this ARIMA model, which stands for autoregressive integrated moving average model, is basically a combination of 3 different models. So first we have the autoregressive part, which is an autoregressive model. Second, we have this integrated part, which means that we are differentiating the data. And finally, we have a moving average model, which uses errors to forecast the model. But don't worry, I'll talk about each of those models in detail. But before I go into that, I want to talk about the notation. So most commonly, ARIMA models are written like this. So you have ARIMA and then 3 parameters, P, Q, and D, where P stands for the lag order or the number of lag observations you are using in the autoregressive model. The Q parameter stands for the difference order, or how often you are differencing your data in order to be trended. And lastly, the D parameter stands for the order of the moving average, which means how many lagged error observations you are using to develop your error AR model. But this is a little confusing right now, I am guessing. So let me talk about each model a little bit more in detail. So we can kind of build up to the ARIMA model. So this is the first part, which is the autoregressive model. It basically means that you model an output value as a linear combination of input variables. So pretty similar to linear regression. However, it assumes that you have autocorrelation and stationarity. So you always have to check for those things. And as I mentioned earlier, you can check for autocorrelation with the lag plot. So in this case, it seems like there's autocorrelation, but we can also see that there is a big seasonal component. And if you remember, if you have seasonality, you can't really use, or your time series is not stationary, excuse me. So you can't really use an autoregressive model in this case for the temperature data. But anyways, the model details look like this. So you have an input variable, which is the yt minus 1 here, and you have a p number of them. So an AR model of p, let's say an AR model of 4, would have 4 lagged variables. So you have yt minus 1, yt minus 2, yt minus 3, and yt minus 4. This means that you are going back 4 observations in time to predict the next observation. And then you also have these coefficients that you need to figure out by fitting the model, but usually the code does that for you, so you don't have to worry about it. One thing I do want to point out is that it is similar to linear regression. I mean, it looks almost the same. You have coefficients and input variables, but the biggest difference is that you are not using least squares to minimize these coefficients. Somehow it's using a different technique, and Lev and I didn't have the time in here to talk about how this works, but please be aware that this is not a linear regression, it's an autoregression, and it works slightly different. Now, in order to forecast, you're simply substituting the t+1 with t, so you're shifting a 1 to the left, and you can use it to forecast the next value in the time series. So this is the AR model, which is the first part in the time series, or in the ARIMA model, excuse me. Now, the integrated part basically means that you are differencing your time series to make it stationary to being able to actually develop an AR model. So even though it's called ARIMA and the I part comes after the AR part, in practice, you always integrate first and then develop the AR model. So it will look like this in the actual equation of the model. You're basically adding an extra term where you're differencing it. And what does the differencing do? If you look at this graph here, which shows the real gross domestic product of the US over time, you can difference this data to be trended, and you can see that, oh wow, actually the financial crisis in 2008 was by far the worst recession we ever had, which is shown by this huge outbreak over here, whereas on the graph it doesn't really look that bad if you think about it. But this is why integrating and differencing can be very helpful in certain situations. But yeah, the assumption it makes basically is that the future change in y is a linear function of the past changes in y. So this is the second part. And the third part is the moving average model. So to understand this, let's assume that you've integrated your data set and that you've developed an AR model on this integrated data set. And now this AR model is this dashed line. And now you're testing your AR model. And for each test, you obviously get an error for each error point. And then you can use these error points to form a new time series. And then this new time series in turn, you can model again using an AR model. And this AR model will give you a forecast for the actual error from the AR model, if that makes sense. Probably doesn't, but let me walk you guys through a step-by-step process how this will work. So firstly, you would create an integrated autoregressive model. You would then go back to the testing data set and get those errors, meaning you would get the error function or the error time series. You would then walk through the time series data test set and calculate the AR prediction for each point, and then predict the residual error using the autoregressive error model to improve the forecast. So what it looked like in practice, it would be, let's say your autoregressive model from the beginning predicted a value of 8, but the AR model of errors predicted an error of 3 for this specific timestamp. This would mean that we have an updated prediction now of 8 plus 3, which is 11. And in theory, this predicted value of 11 should result in a much less root mean squared error score than all the predictions of the original AR model. So yeah, that's in general how this whole freaking beast of an AR model works. There are a couple of tips I found online. Usually your p-value is either 0 or q is 0, and p and q is less than or equal to 0. So people have found all kinds of techniques to look at graphs and statistics to estimate the parameters. Yeah, but in general, you want to keep it simple and don't go crazy on those values. I will show you a technique in just a second to actually estimate those parameters pretty efficiently. Yeah, so this slide Lev provided me, it's pretty dense. So there's lots and lots of information out here. One thing I want to show is that you can create actually different models depending on how you fit in the parameters. So for example, if you have a 100 model, which is an autoregressive model, if you have an ARIMA 011, it's a simple exponential smoothing with growth. As you can see, there's so many different other variables and different acronyms. So if you're interested and if you have time, please check this out. I don't have the resources and the time to explain all of it, but it's a great slide and very useful for sure. So next, the last 5 minutes I want to spend about talking how to find the P, Q, and D parameters. I said that you can look at the graph and there's certain techniques to understand what parameter to best use, but I don't recommend doing this because it's very cumbersome and it takes lots of time. Instead, I recommend you to use a grid search ARIMA where you loop over each parameter and evaluate the model for each case. I'll show you the technique for that in just a second. First, I want to show you real quick how to actually code an ARIMA model with Python. So as you can see, it literally takes less than 30 lines. You're importing all kinds of models. The most important one in this case probably is the stats model, ARIMA model, because this is the actual object you're using to fit. So you're just calling the model, you fit in the parameters, then you actually fit the model, and then you're predicting it, and you're evaluating the forecast and print and plot the final output. So this is how it looks like. Again, I'll upload the slides so you can look at it in more detail. I know I speed through that in very fast speed, so sorry about that. But yeah, again, you can look at it later in your own time. But the point I want to make is that it's actually not that hard to develop it in Python. It's very hard to understand what the ARIMA model does, if that makes any sense. Okay, so now the last slide is focused on the grid search ARIMA. So as I said earlier, you want to iterate over your parameters to find which set of parameters gives you the lowest error score. So here on the left, we're first evaluating the model. So this is just a function that prepares the model and makes predictions. And then here on the right, we're actually writing a function that iterates over 3 different loops for each parameter. So as you can see, we have a loop for the P parameters, for the D parameters, and for the Q parameters. And then we are basically configuring the model for each loop. and printing out the result for each order, as well as the RMSE score. And how this will look in practice is something like this. So as you can see here, we are iterating over each parameter and then printing out the result. And finally, we are seeing, okay, the ARIMA score or the ARIMA configuration of 4 to 1 gives us the best prediction because we have the lowest score. So you probably can go ahead and use this as your final ARIMA prediction. But yeah, that's it. That's all I have. I hope you took something valuable away. And if you have any questions, please let me know. I'm going to stop the recording right now. Let's see if I can do this right now. If I go back to, okay.